So good day everyone, I am Regine Galecha and my topic was all about forces influencing winds and a mathematical look at the geostrophic wind. The two large tanks are connected by a pipe. Tank A is 3/4 full and tank B is only 1/2 full. Because the water pressure at the bottom of each tank is proportional to the weight of water above, the pressure at the three bottom of the tank A is greater than the pressure of the tank B. Moreover, because fluid's pressure is exerted equally in all directions, there is a greater pressure in the pipe directed from tank A towards tank B than B to A. The greater the pressure difference, the stronger the force, and the water moves. In similar way, horizontal differences in atmospheric pressure cause air to move. So, as makita na to sa figure 8.17, the higher water level creates higher fluid pressure at the bottom of tank A and a net force directed towards the lower fluid pressure at the bottom of tank B. This net force causes water to move from higher pressure towards lower pressure. So sa nakita di ba nato nga puno ang tank A which is money na ay higher pressure niya ang net force niya pag mopadung siya diri sa tank B nga lower pressure. Next is the pressure gradient force or PGF. This force arises from differences in air pressure. Air naturally flows from areas of high pressure to areas of low pressure, seeking to equalize the pressure difference. The steeper the pressure gradient, the faster the pressure changes over distance, the stronger the PGF or pressure gradient force, and the faster the wind. So in figure 8.18, the pressure gradient between point 1 and point 2 is 4 MB and per 100 kilometer. The net force directed from higher towards lower pressure is the pressure gradient force. So kani bitaw makita nato nga net force kaning buwa nga kanang arrow mao ni gitawag na nato nga pressure gradient force. So from higher pressure padung siya sa lower pressure. So in figure 8.19, the closer the spacing of the isobars, the greater the pressure gradients. The greater the pressure gradients, the stronger the pressure gradients force. The stronger the pressure gradient force, the greater the wind speed. The red arrows represent the relative magnitude of the force, which is always directed from the higher towards lower pressure. So sa nakita bitaw nato aning sa map view, di ba ang PGF niya mas ning as ang pressure gradient force mas may taas siya. Yeah. The pressure gradient force can be calculated by kanang pressure gradient force equals difference in pressure over distance. So, this condition would produce a rapid change in pressure over a relatively short distance, or what is called a steep or strong pressure gradients. However, if the pressure were to change such as the isobars spread farther apart, then the difference in pressure would be small over a relatively large distance. This condition is called a gentle or weak pressure gradients. So kung shorter distance gali siya, ato ning ginatawag og pressure ay steep or strong pressure gradients. But if the speed if it spread farther apart, then the difference in pressure would be small. So ang ginatawag nila to siya og gentle or weak pressure. So the next is Coriolis force. This force is a consequence of Earth rotation. As the Earth spins, objects moving freely across its surface appears to deflected from their straight line paths. In the northern hemisphere, this deflection is to the right of the object's motion, while in southern hemisphere, it's to the left. The Coriolis force increases with latitude and wind speed. So, the Coriolis force appears to deflect the wind to the right of its intended path in the northern hemisphere and the left to the left of its intended southern hemisphere. The amount of deflection depends upon the rotation of Earth, the latitude, and the object's speed. So in addition, the Coriolis force acts at a right angle to the wind, only influencing wind direction and never wind speed. So kato bitong sa Coriolis effect na discuss naman ni nato atong past nato nga kanang di ba ang aning bitaw sa figure 8.21 on non-rotating platform A, the thrown ball moves in a straight line. On platform B, which rotates counterclockwise, the ball continues to move in a straight line. However, platform, platform B is rotating while the ball is in flight. Those to the person throwing the ball on platform B. The ball appears to deflect to the right of its intended path. So sa platform A, sa nakita nato, di ba, ang ball kay sa gibato na tulid ra siya ang iyang kuan. But sa kaning giingon na deflection depends upon the rotation of Earth, the latitude and the object speed. So sa pagbato na nga ning tuyok siya na siya kanang more bitog ning ang sanay unsa ginatawag ani nato, ang position sa bula kay more pod siya nihiwi mo na ginatawag nato tungod anang sa Coriolis effect. So a brief review. Atmospheric air pressure is the pressure exerted by the mass of air above a region. A change in surface air pressure can be brought about by changing the mass amount of air above the surface. Heating and cooling columns of air can establish horizontal variations in atmospheric pressure aloft at the surface. A difference in horizontal air pressure produces a horizontal pressure gradient force. The pressure gradient force is always directed from higher pressure towards lower pressure. And it is the pressure gradient force that causes the air to move and the wind to blow. So kato nang ginaingon nato nga ang pressure gradient force mo move dyan siya from higher pressure padung sa lower pressure. Steep pressure gradients, tightly packed isobars on a weather map, indicates strong pressure gradients forces and high winds. Gentle pressure gradients, or widely spaced isobars, indicates weak pressure gradient forces and the light winds. After the wind starts to blow, the Coriolis force causes it to bend to the right of its intended path in the northern hemisphere and to the left of its intended path in the southern hemisphere. So in figure 8.22, the relative variation of the Coriolis force at the different latitude with different wind speed. So sa nakita na nato nga nagka-higher bit na, di ba? From 10 to 20 knots to 40 knots niya ang iya pong Coriolis effect ning from 0 paingon sa 0. So try to look at this kani bitang Neymar globe. Except at the equator, a free moving object heading either east or west for any other direction will appear from Earth to deviate from its path as Earth rotates beneath it. The Coriolis force is greatest at the pole and decreases to the zero at the equator. So, greatest at the poles, which is the North Pole and the South Pole niya, decreases to zero at the equator. So, ang iyang net force diri sa equator kay pantay naman siya, mao na siya nga mo decrease gid siya. So next is in figure 8.24. Above the level of friction, air initially at the rest will accelerate until it flows parallel to the isobars at a steady speed with the pressure gradient force balanced by the Coriolis force. Wind blowing under this condition is called geostrophic. So kani bitaw sa makita bitaw nato aning kanang figure, di ba? Ang air parcel niya from high pressure padong siya sa low pressure. Nya ang iyahang ang iyahang air parcel kay mabitaw siya nag-curve pa siya tungod sa Coriolis force. Nya kaning 1 2 3 4, di ba nag-curve pa siya, pero pag position 5 niya, which is the wind no longer accelerates because the net force is zero. So, zero na siya pag-abot sa aning position number 5. So, equal na iyang pressure gradient force ang iyahang Coriolis force. So, when the wind flows in a straight path parallel to the isobar at a constant speed, so when they say constant gali, permanent na siya na speed gali, wala na siya na change, this flow of air is called a geostrophic, which means geo, earth, and strophic, turning wind. Notice that the geostrophic wind blows in the northern hemisphere with low pressure to its left and a higher pressure to its right. So curved wind around lows and high, aloft gradient wind. A cyclone is a large-scale atmospheric wind and a pressure system characterized by low pressure at its center and a circular wind motion. This rotation is called counterclockwise in the northern hemisphere, called cyclonic flow. So when they say counterclockwise, kali binali sa kanang orasan, and clockwise in the southern hemisphere called anticyclonic flow. So kung pareha na siya sa orasan og tuyok, ginatawag na nila to siya og anticyclonic flow. So in figure 8.25, the isobars and the contours on an upper level chart are like the banks along a flowing stream. When they are widely spaced, the flow is weak. When they are narrowly spaced, the flow is stronger. The increase in wind on the chart results in stronger Coriolis force, which balances a larger pressure gradient force. So sa makita bitaw nato, di ba, kung mas broad bitaw siya, more siya wide space kana sa ginaingon na nga kung wide space siya, which is mo weak iyang mohinay bitaw ang iyang flow niya. Kung na siya, kung narrowly space o kung gamay ra siya space, mo strong pud ang iyang pagflow. Same ra pud bitaw anang sa kanang og nay falls bitaw, di ba, og kanang og sa bitaw padung na mo kanang ubos, di ba, gamay naman ang iyang space, mas makusog ang iyang force. Pero og wide gali siya, hinay ra ang iyang flow. So in figure 8.26, by observing the orientation and spacing of the isobars or contour in diagram A, the geostrophic wind direction and speed can be determined in diagram B. So di ba tungod aning isobar or contour pattern kaning sa makita nato sa diagram A, makita na nato ang iyang wind pattern. So in a cyclonic flow in northern hemisphere kani bitang, di ba, pag-abot na sa tunga-tunga kay ang iyang pressure gradient force o iyang contour force kay equals na siya nya. Tungod aning Coriolis force, ang iyang air parcel kay imbis kuan ra siya, nagatuyok ra siya, more siya ning liko mo ning na kuan na to siya nga low pressure area or cyclone. Nya kaning sa anticyclonic flow northern hemisphere equals gyapon iyang Coriolis force o pressure gradient force, pero ang iyang parcel padung sa babaw maong ginatawag na nato siya og high pressure area or anticyclone. In figure 8.30, in the west coast of North America, the wind flow pattern is called meridional, where the wind are blowing in a west to east direction over the eastern third of the United States. The flow is termed zonal. So the geostrophic wind, a balance of force. The geostrophic wind is a theoretical wind that arises when the Coriolis force and the pressure gradient force are perfectly balanced. In this state, the wind blows parallel to the isobar line of a constant pressure and at a constant speed. So kani daing geostrophic wind, ang pressure gradient force ug ang Coriolis force kay equal na siya, or which means kanang balance na siya. So to summarize, the forces that influence winds are complex and interconnected. The pressure gradient force drives the flow of air. So ang dagan di ay sa pagdagan sa hangin, ang pressure gradient force ang nakaingon, while the Coriolis force deflects it. So ang Coriolis force mo'y nakapausab gali, naka-change og direction sa hangin, and friction slows it down. So ang friction mo to'y makapahinay sa pagdagan sa hangin. The geostrophic wind is a theoretical concept that arises when the Coriolis force and the pressure gradient force are in balance. So balance na gali ang pressure gradient force og ang Coriolis force, kinatawag na nila siya og geostrophic wind. This concept provides a valuable framework for understanding atmospheric circulation, but it is important to remember its limitations. Understanding these forces or their interplay is crucial for comprehending global wind patterns and predicting atmospheric behavior. So tungod aning kanang mga force, mahibaw-an na nato kung nabay low pressure or high pressure area nga maoy nakakuan og bagyo. And that will be all about my topic, the forces influencing wind, and a mathematical look at the geostrophic wind. Thank you.